The mole concept addresses the fact that atoms and molecules are so small that when we describe them, we need to use enormously large or enormously small numbers. For example, in 1 teaspoon of sugar, there are about 7 sextillion molecules, that's 7 with 21 zeros, or 7 by 10 to the 21 in scientific notation. And the mass of each of these molecules is just 0.6 sextillionths of a gram, or 6 by 10 to the minus 22 grams. These numbers are so large and so small that they are very inconvenient for chemists, and this is where the mole comes in. A common way to get around large numbers is to introduce a number that represents a grouping of objects. One example of this is the dozen, which has been used since ancient times to mean 12. We are all familiar with what a dozen eggs means, and we can quickly convert to half a dozen eggs or to 2 dozen eggs. When we think about molecules, we need a far larger grouping than a dozen to turn our numbers of molecules into a sensible number that we can work with. The grouping we use is a mole, which is 6.022 by 10 to the 23, or Avogadro's number. And the unit for the mole is spelled MOL. It's still pronounced mole. Even though a mole is much larger than a dozen, it is used in exactly the same way. So half a mole is half of 6.022 by 10 to the 23, just like half a dozen is half of 12, or 6. The principle is the same. A dozen always means 12 of something, and a mole always means 6.022 by 10 to the 23 of something. The only thing that has changed is the scale. So 1 mole of atoms is 6.022 by 10 to the 23 atoms. 1 mole of water is 6.022 by 10 to the 23 molecules of water. And 1 mole of eggs is 6.022 by 10 to the 23 eggs, if only there were enough chickens in the world. The molar mass is the mass in grams of 1 mole of a substance. Molar mass can be easily worked out because the periodic table gives us the mass of 1 mole of each element in the form of its atomic mass. The atomic mass is given below each element in most periodic tables. So let's have a look at a periodic table and zoom in to look at a few elements. Here, the atomic mass of boron is 10.81, so that means that the mass of 1 mole of boron atoms is 10.81 grams. It's important to be able to confidently convert between the mass of a compound and the number of moles. The conversion uses this equation: number of moles equals mass divided by molar mass. You should always take notice of the units in your calculations. Here you can see that the grams will cancel out, leaving us with moles on both sides. So let's look at an example. How many moles are there in 5.5 grams of sodium chloride? We can substitute directly into our equation with the mass of 5.5 grams and the molar mass, which is the sum of the atomic masses of sodium, 22.99, and chlorine, 35.45. This gives us an answer of 0.094 moles. Let's have a look the other way round. Using the same equation, we can calculate the mass of 0.15 moles of sodium chloride. Now we need to rearrange our equation, so mass equals the number of moles times the molar mass. Let's take a look at the units. You can see that moles cancel each other out, and now we have grams on each side of the equation. We can substitute in our 0.15 moles of sodium chloride and our molar mass of sodium chloride, and that gives us 8.8 grams.